Okay, so this is where we were. That if I take a continuous time signal and I sample it and make it discretize in time, the time variable t, which has a unit of seconds, gets replaced by the index of the sample, which is n. And this sample index obviously has no unit. It's just an integer number. But what happens to the frequency also is that it becomes unitless. As you see, this small f is the ratio of the actual frequency in hertz, whose units are 1 over second. But then that is getting divided by the sample rate, f of s. And therefore, it is also a unitless ratio. And it is this small f, which is in some sense different from this capital F. Although we think of small f as the frequency, but we can't actually associate the unit of hertz with it anymore. Okay, so now let us look at those three properties that we had seen earlier and see how those three properties that we had seen over here, the periodicity, the orthogonality, the distinctness rather. I won't focus on orthogonality as much here, but the distinct formulation of S of t when the analog frequencies f are distinct, and increasing the value of f increases in number of oscillations, how those three are getting violated when we consider this discretized time signal. So first of all, this discretized signal, dt signal, discrete time signal sd of n, it may not even be periodic. We saw earlier that in continuous time, s of t is always periodic, whereas s of d of n may or may not be periodic. And the reason is because for sd of n to be periodic, this particular relationship has to hold, that I have to have some integer capital N, after which this sd of n repeats, as shown by this equation. And so if I plug that equality into this cosine function, what it tells me is that the only way that that is possible is this 2 pi f, small f, times capital N has to be some integer multiple of 2 pi. But that happens only if this small f, which we saw earlier is the ratio of the actual analog frequency to the sample rate, f of s. If this ratio is a ratio of integers, remember this k is an integer and capital N is also an integer. So it is possible that the small f is periodic. With the small f, the signal is periodic, but it may not be. Okay, so whenever this f over f of s cannot be written as the ratio of integers, then this sd of n, although it actually looks like a cosine signal as a sinusoidal signal, it may never repeat. It may just take entirely aperiodic, it may become an entirely aperiodic waveform. Okay, so the periodicity is not guaranteed when we go to the discrete time domain. So let us consider this in a little further detail. Suppose we have a total of capital N samples of this discrete signal. Remember, earlier we said that this S of t is infinite in time domain, infinite duration in time domain. Now, when we are talking about discretized signal, we will consider a case where in our signal processor, we have accumulated only a finite number of samples, which is this capital N. Then with this number of samples, the smallest frequency that can be defined is sampling rate divided by N. This is the unit of frequency. And for this frequency, the signal becomes periodic. And the signal, this SD of n, is periodic for all integer multiples of this fs over n. For all values of integer k, where k goes from 0 to capital N minus 1, this corresponding SD of n remains periodic. Because you can see that this k times f1, if I equate it to fs divided by n, then I get this equation over here, for which we have said that this SD of n is periodic. Now, given particular value of capital N and given particular value of f of s, this SD of n is periodic only if the original capital F, the frequency of the incoming analog signal, is such that it falls on one of these k multiples of f1. It doesn't have to be. I mean, basically, the region from 0 to f of s has been itself discretized into n equal parts. And if capital F falls on one of those n parts, then yes, SD of n does become periodic, but otherwise it will be aperiodic. Now, if n is made large, then capital F1 becomes small, and therefore this discretization that is happening in terms of whether the signal is periodic or not of the frequency domain becomes finer and finer. And so it is more likely that the signal remains periodic. Alternatively, for a given value of n and for a given value of f of s, it may be that the signal is not periodic, but if you change capital F slightly, then this ratio f over f of s ends up being a ratio of integers k and n, and then suddenly the signal becomes periodic. And so the periodicity of SD of n may or may not be there. For some values of capital F, SD of n may not be periodic. If you change capital F even slightly, suddenly it may become periodic. So that is one interesting aspect of discretized processing, discretized in time processing. Okay. Now, unlike S of t, for which as soon as you change f even slightly, you get a new signal. For discretized version, it may not be the case. And the reason is very simple to see. I have this equation for SD of n. Remember, this small f is the ratio capital F divided by f of s. Now, if I change f, and if I make it, for example, f plus 1, then what happens is, in this equation, if I make f equal to f plus 1, then all I get is an additional term of 2 pi times n. But that obviously doesn't change the value of this sinusoidal function. And so what we see is that this small f can be replaced with f plus 1 or f plus 2 or f minus 1, f minus 2, etc. The value of S of d of n will not change. So I'm changing f, but for certain changes, that has no effect on the output. And so whenever the signals remain the same, if I change f and make it f plus 1 and I still get SD of n, then obviously for these two different values of f, the signals are not changing. They are obviously not orthogonal. In fact, they are maximally aligned. And other observation that we can make out of this is that the only unique values of f are those within 0 to 1, because as soon as I add a value of +1 or -1 or any integer m, I get the same signal back. So the unique values of small f are between 0 to 1. I can change f. Suppose if my original f is 0.1, I can make it 0.7, and I'm guaranteed to get a different SD of n. So this is called the Bayes range of the discretized frequency small f. Now, it is not that it is the only unique values are between 0 to 1. You can make it from -half to half, or -0.7 to +0.3. But the width of that interval, first of all, you should include 0 in that, because then only it will become Bayes range. And then after you include 0, you cannot make width to be more than 1. You can center it anywhere you want. It doesn't have to be centered at 0. As I said, one possible unique range can be defined as going from 0 and ending at 1. The other can be defined as going from -1 and ending at 0. For both of these ranges, yes, these are the unique intervals. These are the Nyquist Bayes ranges, but they are not centered at 0. So typical convention is to take the Bayes range as centered at 0 and having a width of 1. And such a range is obviously starts from -1/2 and it ends at +1/2. And now any value of small f that falls outside of this Bayes range will actually ultimately be identical to a value of small f which is within this Bayes range. Now this alternatively is expressed as a statement about f of s, because the same observation, if I make it not in terms of normalized small f, which is the ratio of capital F to f of s, but if I instead spell out the actual analog domain frequencies, capital F and f of s, this interval of -1/2 to +1/2 translates to -fs/2 to +fs/2. And so that is called the Nyquist interval. Any analog frequency that falls outside of this Nyquist interval becomes identical to a value which falls within this interval. And that is known as the phenomenon of aliasing that happens. Okay, so now let us take a look at this in a pictorial manner. So this is the frequency axis that I have plotted here in the continuous time domain. And this is a continuous axis, except that I have made it vertical. And what I'm going to say is that all of these blue markers, they are the same once we discretize the signal. And similarly, all of these green markers and the gray markers, they also get mapped to the same value of discretized frequency. So that is what I have shown here in this visualization. And all the values within this Bayes range of -fs/2 to +fs/2, they remain unique, and they end up forming the circumference of this circle. The periphery of the circle is this discretized frequency, and the length, the circumference, is exactly equal to f of s in the absolute sense. In the normalized sense, the circumference of this circle is just 1. It is having a length of 1. And this point for the normalized frequency small f is 0. This is 0.5, and then you come back to 0. Or you say that you begin from -0.5, go to 0, and then come back to +0.5. So So this is kind of a visualized version of the Nyquist Bayes range. Okay. We also said that if I have capital N samples to work with, then this circumference gets divided into N equal parts. And only when the incoming frequency falls on one of those parts, which is a multiple of Fs over N, then and then only the signal remains periodic. Otherwise, the incoming frequency can fall anywhere within this circle, but it will not be periodic signal after we discretize it in time domain. Okay, what this diagram also shows is that as soon as we sample the time domain signal, we end up causing periodicity in frequency domain. This straight line essentially becomes a circle. And when you go around the circle, obviously you are causing periodicity. So the phenomenon of aliasing that results once we discretize the signal is an outcome of a more fundamental effect that happens, which is that the sampling causes the frequency domain to become periodic. Okay, the third property, which was that if you change capital F, the oscillations are guaranteed to change. Even that property is, because of this actually periodicity that happens in frequency domain, that property also gets violated. And so here, I have taken an example that I think I have borrowed from, I forget which textbook, whether it is Oppenheimer and Schaeffer or Proakis and Manokalis. But one of those two textbooks has this nice example which shows that if I have two continuous time signals, one is shown in this red, and its frequency is 9/8 Hertz. So it is slightly more than 1 Hertz. And then I have another sinusoidal frequency which is in blue, and its frequency is 1/8 Hertz. So in continuous time domain, obviously these two signals look different. And this 9/8 Hertz signal has higher oscillations. But if I suppose sample both the signals at 1 sample per second, so f of s is 1 Hertz. Now f of s of 1 Hertz implies that this analog frequency becomes identical to that small f frequency over that I had defined over here. This small f, which was earlier defined all the way back here, if I make capital F of s to be 1, then small f and capital F become identical. So in this particular example, deliberately f of s is taken as 1 Hertz so that the analog frequency and small f become the same. But you will see now that as soon as I sample this signal at 1 sample per second, and this x-axis is showing the unit of time, when I sample both the signal 1 second apart, so you will see these samples I'm collecting 1 seconds apart, then quite surprisingly, the value of the red and the value of the blue are identical at those sampling instants. So the red will give me exactly the same sample value that the blue gives, and that is shown here. The blue and the red intersect with each other exactly at multiples of 1 second. But that is where I'm sampling the signals. And so the red and the blue both will give me identical waveform. So you see that this frequency of 9/8 Hertz ended up being same as frequency of 1/8 Hertz. Once I sampled both the signals at 1 sample per second, which are these circular markers. So this is kind of an experimental confirmation of what we have noted earlier as well, that I can take a frequency, in this case f of a, within the base interval. 1 over 8 is obviously within 0 to 1. And I can add 1 to it. So it becomes 9 over 8. Then this new signal, which is obviously a distinct signal in the continuous time domain, it becomes indistinguishable from the original signal, which is having frequency within the base range. And this is, this experiment can be performed by further increasing f of b. Instead of 1 plus 1 over 8, I can make it 2 plus 1 over 8. So 17 over 8. Or I can make it minus 1 plus 1 over 8. Or I can add basically any integer to 1 over 8, and I will get exactly the same observation. That the blue and the red circles will be identical once I sample at one sample per second. So this is another way of stating that as you increase small f, it doesn't mean that you are going to get higher number of oscillations. Here I increase small f from 1 over 8 to 9 over 8, but I ended up getting exactly the same oscillation characteristic. Okay, now that observation I have actually just spelled it out by a diagrammatic manner. So this horizontal axis is capital F, the analog frequency. And that, as we said, is unique all the way from minus infinity to infinity. Whereas once I discretize the signal, and especially if I consider this normalized frequency small f, which is the ratio of capital F divided by f of s, then I get this periodic structure. There is some base range, and that base range gets mapped to exactly the same range of small f within minus 1/2 to positive 1/2. So this is another way of showing the periodicity that happens once we discretize the signal. Earlier we looked at this by drawing that circle, whereas here I am just, instead of drawing the circle, I am just showing the mapping between capital F, which is aperiodic, and small f, which has become periodic. Is this fine? Yes, no? So Bhavesh is saying that this is fine. But actually I would say this is not fine. There is some problem here. Who can tell me? Something is wrong with this diagram. Any idea? Arushi, what do you think?
Is it the sign ambiguity in the diagram?
Arushi, I couldn't hear you properly. Your audio was not clear.
Audible now?
Yeah, you are audible, but the voice is not clear for some reason.
Sir,
So I
is
think,
it the
sir, capital F and small f need to be interchanged with this graph.
That was Joel.
Yes, sir.
No. Capital F and small f don't have to be interchanged. Capital F is aperiodic. It goes from minus infinity to infinity, and small f is periodic, and so its range is minus 1/2 to plus 1/2. So that is shown correctly here.
Acha.
Uh, so that is not the problem here. Arushi, you were saying something?
Sir, I was suggesting, like the graph, maybe it is upside down or
No, it is not upside down.
or
Sir,
the
at
sign ambiguity.
Anudeep, you have anything to say?
sir, at f is equal to fs upon 2, small f should be half, right?
Okay. Yeah, that is the answer I was looking for. This is Divya, right?
Yes.
Okay, perfect. So actually what I did was I ended up making a mistake. And as Divya has pointed out, see this, if I remember small f is defined as capital F divided by f of s. So when capital F is equal to f of s divided by 2, small f has to be 1/2. But here small f is shown as 0. I think that is what Divya was saying. Am I correct, Divya?
Yes, sir.
Right. The other example is that when capital F is 0, small f can obviously not be 1/2 because it's a ratio of capital F to Fs. So when capital F is 0, that ratio obviously has to be 0. Okay. So this was the mistake I did, but then I didn't correct this mistake. Can somebody tell me how do I correct this mistake now? So I'll correct it right here. Okay, so I'll go to the next in line. Bhavesh, do you know? Actually, Anudeep didn't speak either. So either Anudeep or Bhavesh. How would I correct this mistake? Actually, Divya has already given the answer. So okay. So both Bhavesh and Anudeep are silent. I'll just answer the question myself. So basically, I need to do this. Okay, so now this picture looks better. So when the incoming frequency f is fs over 2, small f actually takes both the values, 1/2 and minus 1/2. Because remember, if I add 1 to minus 1/2, I get 1/2. So in fact, there is a small last point of this line is not present, in fact, if I want to show just the base range. So I will have to say that fs over 2 always maps to minus 1/2. And then there is no value of positive 1/2 anymore. Because positive 1/2 is same as minus 1/2. But if I make this capital F continuous, it will be difficult for me to show that here. So for all practical purposes, there's this vertical line here. And because now if I add capital F of S to this, I get 3 times Fs over 2. So the same discontinuity is apparent over there. Whereas if capital F is 0, small f is obviously also going to be 0. And so it is going to be 0 at f of s, and so it is going to be 0 at minus f of s. Okay, so this is a quick recap of the effect that happens once we discretize the time domain. Now I will probably write up a very quick, I would say, a lab or some MATLAB experiment that I would like you to do if you have not already done it, which is to kind of see this effect. In your previous studies, have you done something like this? Yes, no? Have you experimented, for example, in MATLAB, discretizing a continuous wave signal at certain sampling frequency and then adding 1 to the normalized frequency and seeing that you get exactly the same waveform back? Have you done that experiment yourself? Okay, so Bhavesh is saying no. So I think I will ask you to do that as a very, like a kind of a starting exercise. And then I would also like experimentally for you to verify that this is happening. What this also shows here is that if I go from in the continuous time when I have this continuous frequency capital F in Hertz, as I go from 0 to capital F of S, I am guaranteed to see the oscillations going up and up and up. The oscillations will be smallest when F is 0, basically it's a DC signal, and they will increase as I go from 0 to capital F of S. Whereas in discrete time, the oscillations will increase initially. And then the oscillations will start decreasing in fact. So when you are approaching f of s, going from fs divided by 2 towards f of s, you will see surprisingly that although you are increasing the analog frequency f, the oscillations of the discretized signals are reducing. And then when you reach this f of s, it again becomes a DC signal. So this is something that you appreciate only if you do the experiment yourself. And so I will request you to do that exercise in MATLAB. I'll give you a small write-up, but I think a write-up is also not that necessary. All that I'm asking you is to implement this equation, discretize this small t, make it discrete in time. Obviously, you would have this capital F under your control. And the only other thing that you need to do is have capital F of S also a parameter of your simulator. So I would say fix capital F of S to some constant value, and then change this capital F, the value of analog frequency. And then convince yourself that, I mean, this math is fine. Everybody would get convinced by looking at the math. But still this mapping of this line to a circle, or this particular phenomenon, or this aspect of the periodicity, is something that you start appreciating more if you do this experiment yourself only. Now, after I wrote this part, I realized that there was one other mistake. Remember that S of t, I mean, not a mistake, but maybe a limitation, that S of t I had written it as cosine of 2 pi capital F t plus theta. Now, I realize that when you do the experimentation, it's better to not use cosine function, especially to see this effect. Can anybody tell me why?
So because cos of 0 will be 1.
Cosine of 0 will be what?
So it will take the value of 1.
Yeah, that is
So
fine. That is fine. That we want to see that. We want to see that at capital F of 0, I get a DC signal, which is 1.
yes, yes.
So that is fine. I'm not concerned about that. Well, yeah. So you're right. So cosine of 0 will give me 1. But the other possible limitation of using cosine is that, as you know, cosine is a symmetric function of theta. Okay, are we running out of time or? Okay, I'll conclude in another 20 minutes or so, in case any of you have any other lecture. Okay, so cosine is an even function of its argument. So if you use cosine, what you may see is that the positive value of f from 0 to 1/2, they are identical to negative values of f from 0 to minus 1/2. And so you may actually feel that the unique values are only from 0 to half, not even 0 to 1. Does that make sense? Basically, if you implement cosine function, it may actually give you the same answer for 0.25 as it gives you for negative 0.25. Because in cosine formulation, theta and minus theta are the same. And so what probably we have to use to see this full behavior of periodicity is to use sinusoidal function, because sinusoidal is not symmetric around 0. But the problem with sinusoid is maybe sort of like what Arushi was saying, its value at 0 will be 0. The sinusoidal is also symmetric, but its symmetry is happening around pi over 2. So maybe the best thing to do when you do this simulation is to not look only at cosine. The cosine will properly give you DC value at 0 and Fs and so on. But it has this other problem that it will be a mirror image of 0 to 1/2 and 0 to minus 1/2. And not also use only sine function, because sine of 0 is always going to be 0. So you will the whole signal will disappear. But instead, you would want to use the combination of sine and cosine. It's the combination which is then having this periodic structure. Now, whenever you consider the pair of sine and cosine at the same capital F, that pair of function is analogous to what? So at certain capital F, I don't see only cosine and I don't see only sine. I see both of them together. That is the mental visualization that I make. When I talk about a frequency F, I don't say that it is, I don't say that just, I mean, when I say there is a continuous wave, a waveform, which is a sinusoidal waveform at some frequency F, one visualization is to think of it as sine of that 2 pi ft. The other visualization is cosine, which is 90-degree shifted version. But then the third visualization, which is more complete, is to consider both cosine and sine, both together at this capital F. That is what happens in the electromagnetic wave propagation. You have both cosine and sine going on together in the electrostatic field and in the magnetic field. So when you consider the couple, cos and sine as a couple, what do you get? Any idea?
Sir, like an envelope.
Yeah, not an envelope. Envelope is when you take square root of cosine square plus, square root of cosine square plus sine square. That is when you get the envelope. But when you take the couple together, essentially, you get a complex exponential signal whose, Anudeep said it correctly, in phase and quadrature. So basically the in phase part is cosine and quadrature part is sine. And the actual signal becomes complex valued, exponential of j2 pi fct. Okay, so you want to, when you do this experiment, you don't want to implement either cosine or sine by themselves. You want to implement exponential of j2 pi fct. So it's a complex signal, but it will give you the full picture. And now you can look at both the real and the imaginary part, or the in phase and the quadrature, as Anudeep said, separately and see what is happening. And when you do that, that is where you will be able to see this sawtooth periodicity. Okay, so with that, I will move on now. So this is just one introductory topic that I thought I will mention. And the reason is because this will have some connection to beamforming when we take up that topic later on. Okay, so before we jump into beamforming, let us consider a model of the finite impulse response filter. Its one particular implementation is called tap delay line model. And this is something that I am sure you would have seen earlier. So here there is an incoming continuous time signal x of t. It is sampled at some sampling rate f of s. And so you get its samples which are subscripted by the sample index n, and they are t of s seconds apart. The reason it is called delay line is because these samples are fed to a delay buffer. And typically the FIR filter will have, its length is denoted by capital N. It doesn't have to be this symbol, but let us denote it by capital N here. Then this delay line is called, it is said that this delay line has a length of N. This delay line is obviously made up of the shift registers which make up this buffer. And the output of those registers are multiplied by the weights of the filter, which are denoted as W of N here. And in this delay line, the signals are coming in from the left-hand side, and every sample, the signals are getting pushed out from the right-hand side. And so if I consider any particular sample index N, then the rightmost register will hold the oldest sample, x of n, at that sample index n. And the leftmost sample will be the newest sample. It will be n sample earlier than this x of n. So that is how we are denoting the set of samples that are within this buffer. It's essentially a vector. And the index of the samples inside that vector is denoted like this. We typically think of this n as a variable. N is, remember, analogous to time. So n keeps on changing with every sample duration. But the formulation of the samples inside the shift register is always this x of n. The filter weights, we say they don't change. They are constant. And so this particular type of filter is known as time invariant or shift invariant. And that is why if you see here in the weight of the filter, I don't have a subscript n here anymore. In the this capital W, sorry, bold-faced W. I actually have this small n here, which is my mistake. I should replace it by some other variable. This small n is not same as this small n. So that was my little clumsiness here. And finally, the filter output is given as this inner product between the filter weight vector W and the buffered samples. And this is a Hermitian dot product because this W and X are in general not real valued. So I have to take Hermitian transpose. But essentially, I am taking this summation. So you will see here that this W does not depend on N, only X depends on N. So I should call here this W of small m. Does this formula remind you of something? The formula for the filter output? This is called what formula?
It's a convolution.
Yeah, so this is nothing but the convolution formula. Okay, so now I'm just going to draw a diagram of this step delay line. So this is those registers that I was saying. The signal is coming in from the left-hand side and it is going out on the right-hand side. And at the output of each of the shift registers, I will have one sample of the incoming signal. And I'm going to tap the output of, or the input rather, of each of the shift registers. That is where this word tap delay line comes. So this tapping I am indicating by these triangles. And after tapping the shift registers, I am multiplying it by this filter coefficients, these weights. And then basically I just add all of those weighted samples and I get the particular output of the filter. So this is the tap delay line model of the FIR filter. Okay. Now I'm going to ask a question which is very specific. This is a general formulation. Any FIR filter can be represented using this equation, the convolution equation, and it can be drawn using this step delay line model. It's a very general model. This is, by the way, a model of linear shift invariant or linear time invariant system. The shift invariant part comes because this vector W does not have subscript n, unlike the input. So it is invariant to the shifts in the time. It's invariant to small n. And it is obviously linear because this operation is all linear. Now, I'm going to take a very specific case of this filter now. And also I'm going to take a very specific case of this input. So from now on, from the next slide onward, what I'm going to describe is a very specific realization. But we will see what is happening for that realization. And so what I'm going to say is that what if my filter weights are given as this complex exponential, this pair, this doublet or couple of sine and cosine, where the small, where the normalized frequency is small f. So we are considering a specific type of FIR filter whose coefficients are given by this exponential function, the complex exponential function. And you will notice that instead of calling this now as W of small n, I have made it little more explicit. I can continue to call it as W of n. There is no problem with that. But I am now going to call it, I'm going to denote, give it a notation where the subscript denotes the length of the filter, n, capital N, and then superscript denotes the index of the coefficient. And here again, I have clumsily made the mistake. This small n should have been small m, because if I am saying that n denotes this time variable, then here I'm not talking about time. This is definitely a shift invariant system. So this is I'll correct this mistake in the updated version of the slides. So the small n will be replaced by small m. But anyways, so this first symbol here in the superscript denotes the index of the coefficient. And the second symbol f denotes this normalized frequency, which is, as we have seen earlier, its unique range is only between negative 0.5 to positive 0.5. And both the endpoints are not included. You have to include only one of the two endpoints. So in the vector form, we are going to denote it as capital W of small f, capital N. This is correct. Here I removed the dependency on n. Basically, I'm considering this coefficient vector as simply a vector of complex exponential signal whose samples are given by this. Now, I want you to keep this in the mind because we will be using it later on. So this bold-faced W, subscript n, superscript f, always will denote this vector. Okay? So we are considering this specific FIR filter. And now, not only that we will be considering this specific FIR filter, but we are saying that its input is also specific. So the input to this filter is also the specific input, which is also a complex exponential, but its frequency is some other frequency, f naught. The other change I made is I removed this negative sign here for the sake of mathematical convenience that will become clear later on. Okay, so there are specific filter coefficients that I'm considering and specific input to the filter that I'm considering, and both of them have the same form. They both are complex exponential functions. So what is the output of this filter when the input is this frequency f naught? So what we can do is we can write this W, which we already have, but we can also write this x of n as a vector when x of n has this formulation. And so that is what I have done on this slide, next slide. Because both of them are complex exponential, there is a great similarity in the notations of the buffered samples and the filter coefficients. The only difference is that this buffered samples will have this time variable present, whereas the filter coefficients, there this n is not representing the continuous time at all. So that is what I have done here. This is the filter coefficient vector, W, capital N, small f. Same as what was shown on the previous slide. This is the buffered sample vector. This is the vector of samples in my tab delay line. The only thing that I did is I took out x of n. Remember, the last sample, or you can call it the first sample, whichever way you look at it, whether you go from left to right or right to left, is always x of n. So that x of n is here. This one here is x of n minus 1. x of n minus 1, I can write it like this. This is x of n minus 2. And finally, this last entry is x of n minus capital N plus 1. So this vector, for the specific case when the input is this, can be written like this. But you will see that this is nothing but W of n f naught. It is actually same as this W n f, except f has become this incoming frequency f naught. And so now y of n is the Hermitian product between the filter weights and the tap samples. And so it becomes this. And so what we see is that the output is a scalar, y of n, and it is a dot product of these two vectors, w at frequency f and w at frequency f naught. And they both are of the same length, and that is why we can take the dot product. But we know that when we take dot product, we get again a scalar. It may be complex valued, but it is ultimately a scalar. And so that is why the output is also a scalar. Basically, the input scalar x of n. Remember, x of n is the nth sample of the input. It's a scalar. That scalar is getting multiplied by another scalar here. And so obviously what you get is output, which is y of n. Is this fine? I'll stop in another 5 minutes, okay? Okay, so what we are going to do now is look at the specific form of this dot product. X of n we know already, and y of n is the output of this operation. But let us see what this dot product gives us. Okay, so I have this trick here so that this derivation becomes not too much for you to follow. If I flash it in one shot in front of your eyes, you will be lost. So I'm going to step in a stepwise manner. I'm going to kind of try and unerase the parts. Okay, so this is just the writing this dot product in a summation form. This is nothing but our familiar convolution operation. Okay, so that is fine. Now in the third line, I substituted w of m and x of n minus m. So here, as you can see, w is no longer a function of small n. So this part is correct. The earlier notations, I should just replace small n of 4w with small m. So once I do this, I get this formula. You will notice that w had minus sign in front of the exponent, a minus sign inside the exponent. And so when I take this complex conjugate, where this complex conjugate is coming because of the Hermitian operation, that minus sign becomes plus. And then this second exponential is just the formula for x of n minus m, where only thing I did was I replaced n with n minus m. So now I notice that this first part is not dependent on small m, so I just pull it out. And then the two other terms which are dependent on m, I combine them. So this is f and this is minus f naught. So I get this formulation over here. But now I notice that this is nothing but my original input x of n. And so this is my final answer, that I get y of n, which is x of n, multiplied by this expression over here. This is nothing but the inner product between w of f and w of f naught. And what we have shown here is that this inner product ends up being the summation of the samples of this complex exponential, except the frequency of the complex exponential inside this summation is neither f nor f naught. It is indeed the difference between the two, f minus f naught. So the final answer that I get is that I get x of n times a complex scalar, which is the inner product between these two vectors. But that inner product, which is a complex scalar, which I have denoted as capital W, is a function of capital N and this difference frequency. Is this fine? Any question here? So if not, I will go to the next slide, which will be the last slide for today. So in this slide, oh, okay, fine. This is one remark that I want to make, that this WNF naught is the amount by which this filter will scale the input. This is a scaling in the complex manner. Wn is in general going to be complex. So, okay, maybe 2 more slides, okay, but I'll end very soon. So I have a formulation that filter output is x of n times W of capital N. So output is in the form of x of n times alpha, where alpha is just a scalar. So way to think of this is that my input x of n actually appears directly at the output, except it gets scaled by alpha. In case if this alpha, which is W of n delta f naught, is real valued, then the input gets attenuated. If alpha becomes 0, then I don't get anything at the output. If alpha is greater than 1, then actually this filter ends up playing a role of an amplifier. But in either case, I am getting the sample x of n directly coming out at the output. In general, alpha may not be real valued, and so there will be an additional phase shift that will be present. And the final observation that we make is that this alpha is going to be a function of capital N and this difference frequency delta f naught. Okay, so now our focus is on the expression of this Wn, delta f naught. So for that, I'm again going to flash in front of you a bunch of derivations, but should be not too difficult to appreciate. So I'm generally going to define a function Wn of x. Remember, this is that complex scalar as this series sum of this complex exponential as a function of this small x. Small m doesn't appear at the output because it gets summed out. So I will write this as z to the power m, where z is exp to the power j 2 pi x. It's just because now when I write it like this, you will immediately recognize from your high school math that this is nothing but a series sum, a geometric series sum. So it has this particular answer. Once I get that, I will obviously play some tricks on it, and I will pull out n by 2 in front and z to the power n by 2 in the front in the numerator and z to the power 1/2 in the denominator. And so I get this expression. Obviously, this fourth line is identical to the third line. And so now after doing that, I'm going to multiply both the numerator and the denominator by -1. And so I get this expression. Now I will plug in the expression for z that I had used earlier. I didn't have to do that. I could have just continued with this exponential formulations, but then this 3 lines would have become pretty long. So this was just a notational simplification. Once I do that, what I realize is that the numerator and the denominator look a lot like sinusoidal functions. And so I'm just going to replace them by sinusoids. This numerator part is going to be, after I divide it by 2 pi x n divided by 2, I get sine of 2 pi x n divided by 2. And similarly, for the denominator, I get sine of 2 pi x divided by 2. Except I have to put a multiplier capital N here. So that is a mistake here. I have made a derivation mistake, except that capital N came back, thankfully, in this line. You know what? Actually, the mistake is that this line should not have been there. This should have been the last line. So just pardon me. From this line of the equation, we should go to this line. And now you will see that once I get that, I finally get this expression over here. Sine 2 pi x n over 2 is divided by nx over 2 is sinc function. And there is another sinc in the denominator. And then there is this capital N sitting out front because here I have put capital N in the denominator to make this to be a sinc function. Okay, so this is kind of just a lot of derivation here, but there is nothing fundamentally conceptually new here. Okay, so the last thing for today is that this equation here is a very important equation that frequently appears in the DSP topic. And then the result that we got of simplifying this W capital N of X is probably one of the most fundamental equations of digital signal processing. Okay, so this is where we will end today, and we will meet on Wednesday at around 10 o'clock in the morning. So see you then. And in between, I will try to write this lab experiment that I had asked you to do. And you will see that on our Google Classroom. Okay, so if you have any questions, you can ask me now. Otherwise, I will end today's lecture.
Sir, can I just see the slide number 10?
Okay, slide number 10. Yeah. What is the question?
Sir, is there a representational mistake in X and W and the summation? WM conjugate Xn minus M?
It could be, yes, it could be. So, so when m is 0, I have x of n times w of 0. And when n is capital N minus 1, I have x of n minus n plus 1 and w of n minus 1. So what is the mistake? Oh, this w has to be complex conjugated here. Is that what you are saying?
Sir, when m equal to 0, it's W0 conjugate
Yeah. So,
and multiplied with xn, right?
yeah, so it is getting multiplied with x of n.
But sir, the matrix representation that you gave just before that,
Matrix representation?
the vector, sir, the vectors are represented, no sir, the same slide.
Yeah.
So the same slide, xn is represented as xn minus
Oh,
capital
okay,
N.
okay. Yeah. So this x of n should be put up front here. So this this vector x of n should be flipped left, right. Is that what you are saying?
Yes, sir, yes.
Yeah. Okay, thank you for pointing that out. So there are two mistakes here. This x of n should be flipped, and this w should be complex conjugated on this figure. So this mistake is not present over here. You will see that here it is matching correctly.
Yes, sir.
Okay, so good point. I'll make those changes. And okay, anything else?
So, I have a question. So, when we are
Yeah.
replacing the weight with the exponential function, so can we say that we are doing like endpoint DFT of xn?
Excellent point. Excellent point. So that is where we will go to in the next lecture.
Okay.
You are right. Short answer is that you are right. Okay, anything else? Okay, fine. If not, then I will end this session, and then I'll see you in a few days. Bye.
Thank you, sir.